Okay, hi everybody. Sorry, we've had some problems with YouTube, but I think things are working now. So thank you for joining us. I think some people are probably still stuck waiting for the YouTube to refresh, but thank you for those who've persevered. So should we start or should we wait a bit longer? We can start.
Yeah, we can start with some introductions.
Okay, so my name's Andy. I'm from Grillo.
Hi, I'm Michael. I'm the data scientist at Grillo.
Hi, my name is Luis, and I'm the seismologist here at Grillo.
I think you're going to have to come in.
Yeah. Okay, good.
Perfect. So today we've got an agenda. We're going to try and keep things very short because there's a lot to get through, and I think everyone's quite busy. So we're going to talk you through a couple of things related to OpenEEW, what it means. And so if we could have the presentation up, I don't know if that's possible. I think you have to press the present button. There you go. And you have to transition. Yeah. So we're going to talk about OpenEEW. We're very excited. This is a whole new initiative for us. We've been working with earthquakes and technology for about 4 or 5 years. And we made this sort of very important decision recently that we're going to share what we've done, and there's some very, very beneficial reasons which we think will make this very exciting for everybody. So on the screen, you can see the agenda that we have, and I think we can put the little video up as well now of the people. We're going to see the agenda, and you're going to be able to. These are the different things we're going to talk about. What is an earthquake early warning system? Some people watching now know exactly what an early warning system is, but we're going to define it from the way we see it and the things that we've already accomplished. And then the next stage is, I can't see. Sorry, what is an early warning system? And then we're going to talk about OpenEEW, and we're going to talk about, sorry. Yeah, give me 1 second. If you can explain a little bit about early warning systems, Michael.
Yeah, so first we'd like to just introduce the concept of an earthquake early warning system, because now we're very familiar with this, but when I first came to Mexico, I had never heard of this concept before. So basically, the idea of an earthquake early warning system is to send alerts to people or devices to tell them that shaking caused by an earthquake is about to occur.
Okay. Sorry, just trying to get the agenda up.
Maybe you can show it from here. It would be better. No?
Yeah. I think, yeah. Yeah, sorry. Give me 1 second. I think what happened is that we made this screen too big.
Done. Here.
Okay.
Okay, well, there are a few elements that defines an early warning system for any natural disaster, but in this case we're going to focus on the ones for earthquakes because that's what we do in Grillo. And okay, are you ready?
Yeah.
Cool.
Okay. Sorry. There we go. Done. Okay, good. Sorry, guys. Okay, so what's an early earthquake warning system? How we built the warning system that we've created both in Mexico and in Chile. Why we've created OpenEEW and what it really means. And what we're actually doing in OpenEEW, we're sharing a whole lot of data, which we're going to talk through. Then Michael and Luis are going to go through a very, very, very quick tutorial, and you're going to see exactly how you can interact with this data. And then the next steps, because we're actually going to have a series of webinars and a series of launches, and we're releasing bit by bit all the different components of our early warning system. But today, the big announcement today is that live right now is the data which we've collected for a long time. So if we can go to the next slide. Great. So just very quickly, earthquakes. Most people here, I know, are interested, work in the field in one way or the other, and they are devastating natural disasters. Many fatalities and injuries. They have an impact on economies, and we are right now talking to you from Mexico City. And here in Mexico City, we've had a lot of very significant earthquakes, including 2017, which has really inspired part of what we're doing today. So in the next slide, you can see an EEW. What is an EEW? So an early warning system, it doesn't predict earthquakes. It tells you when they're already happening. And a network of sensors record ground acceleration, and in our scenario, and we then do some calculations to work out if it's an earthquake or if it's a non-earthquake event. And if it's an earthquake, we then warn people who are in the path of the shaking.
Here are a few components that I was talking before. So the components basically that we use to detect earthquakes is the seismic network. And for that, we use hardware, which are sensors that we develop as well. The second part is the transmission of the data in real time in order to detect the earthquakes on near the epicenter where the earthquakes are happening. In the case of Mexico and Chile, this happens most of the time, or the largest earthquakes that we have in the Pacific coast. And then the third component is the notification, which is the different type of channels that we use to communicate people that an earthquake is coming. And if you are far from the place where we detect the earthquakes and where we send the notification, you have a time, a window that allows you to activate protocols, to do some things, and basically save your life. That's what we.
And I think it's important that the non-seismologists understand that this window is very sort of it's very fixed, because we start when the earthquake has been recorded, and then we have a limited amount of time before it reaches other places. So the utility of an EEW is related to how much time people will get from when the shaking has been recorded.
Right, and for the non-seismologists as well, this is happening because basically the transmission or the signals that we are using through internet or other channels travel faster than the seismic waves. That allows to have this window of time before you start feeling the earthquake actually.
So on the screen you can see now some important regions around the world, countries. So early warning systems obviously are incredibly important in places where you have a lot of fatalities. So we've colored in blue on the map countries which have experienced more than 1,000 fatalities due to a single earthquake. There's a lot more countries that have earthquakes and have significant fatalities, but we're talking about very, very destructive events that have occurred. And so so you can see there's a lot of countries. Now, the ones that are in dark pink, which is really just Taiwan and Japan, are the only countries here that have a complete early warning system. The ones that are in the pink have a sort of partial system, regional systems. So you can see there's a lot of opportunity to create early warning systems in countries that really would need them. Great. So the components of the early warning system that Grillo built, which is really what we're going to share with you today and over the next series of webinars, is the sensors. This is the key component to the network that we use to detect. And we will go into more detail in the next webinar where we talk about the sensors. But effectively, they're Internet of Things devices that we've created in terms of the hardware, the schematics, the PCBs, but also in terms of the firmware. And what's interesting about the sensors is that they transmit raw acceleration data. So other types of early warning systems, what they do is they do some level of processing on the site, which means to say they take acceleration data and they make some determination about whether it's an earthquake or not. We don't do anything of the sort. We actually put a lot of work from day one into streaming all of the data, which actually makes what we've got in the cloud very valuable. So today you'll be able to see raw acceleration data in AWS. The next stage is the detection algorithms. And so Michael, Luis, and the rest of the team have developed ways that we can, in real time in the cloud, as we're streaming this data with very little latency, we can determine if it's an earthquake. And then we have different ways to notify people using alarm devices and apps.
And sorry, I'll just comment that the fact that we're sending unprocessed accelerometer data means that we have a lot of flexibility to try out different algorithms on historic data. So if we were just sending some sort of processed data, then if we wanted to then go back and try some other algorithm, we'd be limited to whatever processing we'd done. But this way we're completely open to trying different things at any time.
Okay. So this is the last slide from me. This is just what we're doing with OpenEEW. So I think at some point we realized that Grillo, as a sort of social enterprise, has a limited reach. And whilst we created something in Mexico and last year in Chile, there's a lot of countries like Nepal, Italy, Turkey, and other places that could benefit from what we've already done and create parallel networks. And really, we're just interested in having more people have access to this type of technology. So that was the catalyst, understanding the limitations of what we can do and reaching out to community to not only deploy similar systems, but maybe help us make better ones. And in terms of better, we mean better sensors, better algorithms, better ways of notifying people, and finally, a sort of less technological, but creating guides as to what people have to do, a sort of standard guide, because every country has unique discussions about that. But of course, we want to stimulate parallel networks, and we also, so we have the core mission. So do you want to talk about the data, Michael?
So as we mentioned, since we deployed our network at the end of 2017, we've been collecting unprocessed accelerometer data. Until recently, this was just accessible by ourselves, but we realized the great value that this data has. And we decided that to really to fulfill the potential of this data, it made sense to open it up to the world. And so that's what we did last week, as we published all of our accelerometer data dating back to the end of 2017 as an AWS public dataset. So what this means is that our 700 gigabytes and constantly growing set of data is now open and accessible to anyone to use. It's as we mentioned, it contains unprocessed accelerometer data, and so there's really no limit in terms of what people can do with this, whether they're seismologists or data scientists or anyone else who likes playing with data. There's something in it for them with this data.
Can you explain about the actual data itself? What's actually in it?
Yeah, so we're sending data from accelerometers. So there are 3 axes, the X, Y, and Z. Each second, the accelerometers sample about 32 times per second. And so every second, we're collecting about 32 data points from each axis. So essentially, we have a very large set of data with this X, Y, Z values and a timestamp corresponding to them.
Yeah, I would like to add that it's not only we have a set of data that is in continue and real time streaming. So we have what we call in seismology in other areas like noise. Not only we have recorded earthquakes that goes within this magnitude range between 3.7 and 7.2, but also a lot of noise. And in that noise can be another type of signals and interesting people for for the data scientist or people that is interested to play with the data.
I think it'll be interesting when we get to the hardware webinar. We can talk about how we locate our sensors, because this noise, a lot of these sensors are inside buildings in rural areas of Mexico and also in Chile. So a lot of noise might be someone slamming a door, a car next to the house. So they are noisy areas. Although having said that, we've had we've had great success in extracting earthquakes from this noise. But we think there's an opportunity to get even better with people like you.
I mean, the noise is part of the vibrations, but actually the signals are quite clear when an earthquake it's detected by the seismic network.
Yeah, and and another thing to mention is if we just selected the data that we would record, we'd select large motions, but we might miss things that we thought were just noise, but there might be some hidden patterns in the data. And so opening up this data now, we can try to discover things that appears to be just noise, but could be actually the beginnings of an earthquake, for example.
So Michael's been working on this Python library, and I think we're going to get a tutorial now. So here we're going to get away from the presentation screen, and we're going to show you. If Chloe could just shut down the presentation, and what we're going to do is show you the browser. And here Michael's going to take you through an example of how our Python library works. And this Python library is going to let you interact with the data set we've just published. Okay, so Michael.
Yeah, let me move.
Yes. Okay, so
good.
Yeah, this is just a quick tutorial just to give an idea. To give an idea about what's possible with this data and how easy it is to get started.
Okay, I'm just going to make it so everyone can see the size of the data. Okay, tutorial. Okay. So where can people see the tutorial now?
Yeah, so we're going to... this tutorial has been presented as a Jupyter notebook using Python. Now this will be made available on our GitHub page, and we'll put a link in the YouTube video. So you'll have a chance to go in it in more detail later. Okay, so we begin by just importing some packages. Now these are fairly standard, but the key one here is this OpenEEW Python package, which we just released last week to coincide with the release of our data. So the idea of this OpenEEW Python package will be a way to facilitate working with all aspects of OpenEEW using Python. So this will cover the data, the sensor firmware, detection algorithms, and so on. Currently, just because we're starting with the data, the package currently deals just with the data and makes it easy to access.
And to install it, they just do pip install, right?
Yeah, so this is available to install using pip in a very common way. Again, the links will make this clear to the YouTube video. Okay, so for this tutorial, we're just going to have a look at an earthquake that occurred last year, a 7.2 magnitude earthquake that occurred in Mexico and was felt in Mexico City. Okay, so the Mexican Seismological Service, or known as SSN by its Spanish initials, has a complete catalogue of earthquakes, and so these details were taken from their website. Okay, so we had this earthquake, its coordinates, we had the latitude and longitude, and also the date in UTC format. Okay, so the first thing that we just want to do is just to have a look at this epicenter on a map. Okay, so we can easily do that here. This occurred on the coast of Oaxaca. Okay, and just for people who are not so familiar with Mexico, if we zoom out a bit, we can see that Mexico City is here. It's about kind of 400 kilometers or so away from the epicenter. Okay. Okay, so the first thing we're going to want to do is to get some data that corresponds to this earthquake. Now, to do that, we initialize a so-called AWS data client, which is part of the OpenEEW package. And to initialize it, we just need to specify the country we're interested in. So that's Mexico in this case. Okay. So having initialized this data client, we can start to get some data using it. Okay, so the first thing we want to do is to know which sensors we had at this time. Okay, so this OpenEEW Python package gives an easy way to find this with this method get devices as of date. Okay, so this gives us a list of devices with device ID and latitude and longitude. Okay, so this tells us essentially where each device was at the date of this earthquake. Okay, but in this list, it's a bit hard to understand what's going on. So we scroll down past this long list of devices that we have, and we visualize it on a map. Okay. Okay. So as we see in this map, most of our sensors are deployed along the coast of Mexico, which is the most seismically active region. Okay, so we see here the epicenter, and we see that we have several devices close to the epicenter. And if we click on them, we can see the device ID. So here we have 4 and 6 and so on. Okay. Okay, so now we know. Where the devices were at that stage. We want to actually get the data that these devices were giving us. Okay, so this is also made easy using the OpenEEW package. So firstly, we specify the start and end date in UTC format. And here I've specified a 4-minute window around the time of the earthquake. And then we just use this method, get filtered records df, to get the records as a pandas data frame. And then I do some other modifications to this data frame. For example, I get the sample time as in a date time format instead of Unix time. And I just select the columns I'm interested in. Okay, so here we can just get a quick look at this data. So we see we've got the device ID, the XYZ axes, and then the date time corresponding to the sample points. Okay, so the next thing that we'd like to do is just to plot this data and just see what was being picked up by each sensor. Okay, so I just quickly here did a function that's going to plot the data for a single device ID. Okay, now if we just go back to the map quickly, I think it makes sense to start with the sensors that were closest to the epicenter. Now the one that was closest was this 4 station, but unfortunately at this moment it was not sending data because just by the nature of having a seismic networks, at times some sensors stop sending data and then they come back. So that's one of the challenges. But the next sort of closest one would be this one, sensor 6. So let's have a look at this one. Okay, so here I just pass in 6 to this function I did, and we get some seismograms. And you can see that there was definitely the earthquake was registered. Now this red line here shows that the start time of the earthquake itself, and you see that there's a slight delay to when it's being recorded by the sensor of about 10 seconds. And then we start getting some very large acceleration values. Okay, so that was for the sensor that was closest to the earthquake. Now it's interesting also to think what was happening in Mexico City. How was this detected in Mexico City? So if we go back to the map, we can see that we had a sensor in Mexico City with ID 0. So we're going to see how the earthquake appeared to this sensor. Okay, so this was the sensor 6 close to the epicenter, and now if we see sensor 0, we see that it looks similar to sensor 6, but there are some key differences. Firstly, the acceleration values are not as large, which you'd expect because it's about 350 kilometers away. And secondly, that the time before the earthquake is detected is much later than it was for sensor 6. So with sensor 6, it was about 10 seconds after the start of the earthquake, whereas with sensor 0, it was about a minute or so. And so this is one of the key kind of aspects of an EEW, the fact that in faraway locations, the time before the earthquake is felt can be up to a minute or more. And so this gives us a window of opportunity to alert people. Okay. And just continuing a little bit on the theme of distances and acceleration values, we can just here get an overall look at how the acceleration values differed by distance from the earthquake. Okay, so firstly, I just get the horizontal acceleration using the horizontal axes of each sensor. And then for each one, I work out what the maximum acceleration value recorded during this earthquake window was. And if I sort that by descending order, we see that, as expected, sensor 6, which was the closest, had the highest values, and then they start decreasing steadily. And just to formalize this a bit more, we can compare this to the distance from the epicenter. So here I just, for each device, I calculate the distance from the epicenter. I combine it with the PGA, the peak ground acceleration. And then here I just sort them by the distance from the earthquake. And we can see that as the distance increases, the PGA values are generally decreasing, as we'd expect. And if we just plot this on a graph, we can see the relationship here. So there's a exponential decrease in the PGA value as the an exponential decrease in the acceleration values as the distance from the earthquake increases. But so I think it's not possible to see that at the moment.
The plot it's just below. Yeah. Anyway, this is an example of standard things that can be done in with the data, seismic data. Typically, this is what seismologists and hazard modelers they do. They just basically compare acceleration with distance and to see what are the effects at different distances in order to estimate what will be the shaking, which is at the ultimate state what we want to know. How strong is going to be an earthquake at a certain location, and use that in order to warn people. So there are many things that can be done. This is as I mentioned, and as Michael beautifully explained, this is one of the most common things that can be done. But there are many other things that, or parameters that can be estimated or discriminate between what Andy was saying before, like anthropogenic noise, somebody slamming a door, somebody walking around, and actually to use all the signals that we have in order to estimate when it's an actual earthquake, and the estimation of if that earthquake is going to have an impact at certain distances. And the challenging part is to do all this in a very the minimum amount of time in order to warn people and to give different type of warnings.
Yeah, I think to some extent the characterization of the earthquake is more challenging than the detection parts. The detection part is fairly straightforward. Well, it can be more challenging to reduce false positives, for example, but I would say the real challenge is, given that an earthquake is occurring, to quickly determine who should be notified, if anyone.
And another challenge that we've always faced is trying to reduce the number of sensors we need to issue an alert. So, it's safer to wait until the earthquake is detected, is triggered by a number of different stations. But using machine learning and other methods, we might find a way to do a sort of very, very accurate detection with just a single station, and that's something that I think our data would allow you to experiment with. So on the screen, we've got a sort of timeline. So today we've done the first stage, which is the data, and so thank you very much to AWS who have hosted this data alongside other great data sets. On the next webinar, we're going to be releasing in about a month or so some schematics, and that will be the sensors. You can make your own sensors. So we're going to be offering blueprints and the sort of 3D models as well that we use for the cases, some Gerber files, some PCBs, some firmware examples. So you can just go ahead and make them. Now we've experimented with different accelerometers. So we're going to give you an example of one accelerometer, but we've honestly tried all of them. So you'll be able to do that. And we're also going to release at the same time something we've been working on, which is a sort of an alarm device as well, which will allow for very low cost people to have an IoT alarm device. Then the next stage will be the algorithms, and we're going to again on our GitHub publish what we do to detect, and we'll have some architectural suggestions for how you can recreate what we do in the cloud or even on a laptop. And then finally, we're going to have a sort of more sociological element, which is guides, because we love technology, and often EEWs are left in the hands of people who do technology, and actually it's a lot more than that. There's an education element involved, what people should do, what people shouldn't do, and so that's going to be the final part of this series.
Yeah, I would like to add something related to the algorithms, which is very important, I think. So I would like to the community to join the discussion, because it's true that the components are the same, but to adapt it to different places, that's also challenging. No, the distribution of sensors, how we detect earthquakes in Mexico, it's slightly different the way that we do it in Chile for different reasons. And I think that's part of what we want to also, to engage the community with discussions, scientific/technical. That will be great for everybody. And we do believe here, as part of our philosophy, is that earthquakes, they don't have borders. No, they just basically pass to the political borders. So they affect us all, no matter like this imaginary division. So I think make it bigger, the community in other countries, that will also make us stronger and resilient.
Next slide. So just some ways that people can get involved. So we've created a forum. It's in community.grio.io. It's just a forum which is just started. We would love for you to join. That's a place where people can post questions, and we'll be very active in responding. Anything, how can I access the data? A question about the tutorial Michael did, a question about the data itself, a question about what we're going to be doing in the future. Then we can read some articles. We've written a number of different articles in Medium, blog posts, and we talk about the history of what we've done and different aspects of EEWs. We've got a GitHub repository where you can visit, and then we always are available by email as well. So I think that's enough.
Yeah. Yes. I just would like to add that, the dates that you already mentioned, I don't know if the presentation is going to be available for the people to download.
Yeah, so both the presentation and this video are going to be available for people to download.
Yeah, in order for you to check where the next dates or when we're going to have another webinars. And and ending at least in the first phase with the release of guides or the discussion of guides for earthquake preparedness that is coming in September this year.
Yeah, September's a big deal in Mexico because it's the anniversary of 2 of the major earthquakes in the last 30 years. So in September, it's when we will complete all of these components and have them available to people.
Okay, Chloe's telling us about the questions.
Yeah, if they have any question, feel free to ask right now.
Any questions, anybody? You can type them in to the chat. If not, I think that would be. No questions.
I don't see no questions.
I think we covered everything very well, so no one has any questions. Okay.
They're very confused. I don't know.
Okay. Maybe some people thought we'd be doing this in Spanish. Maybe, I don't know, another time. Gracias. Thank you very much.
Thank you.
Thank you.
Thank you very much.